Imagine standing before a giant pyramid. You want its height, but you can't climb it with a ruler. The problem is measuring distances you can't physically touch. The solution begins by picturing an invisible triangle between you, the top, and the base. Ancient Egyptians needed pyramid heights for construction. Sailors needed distances to shore to avoid rocks. Astronomers wanted to map the sky. A simple ruler couldn't answer these, so they invented a way to turn a line of sight into a measurable shape. Stand back and look at the peak. Your eye, the peak, and the base form a right triangle. The ground is one side, the height is another, and your sight line is the long slanting side. If you can measure one side and you want the height of a tree, walk 20 steps back from it. Look up at the top, the angle between the ground and your sight line is 45 degrees. At 45 degrees, the triangle's two short sides are equal, like half a square. So always sketch the triangle first, label what you know. The most common mistake is swapping the height and the ground side. A quick trick: if you can step back until the angle looks like 45 degrees, the height equals your distance. Today, try measuring. An angle is simply the amount of turn between two straight lines that meet at a point. Imagine opening a book, the cover and the first page spread apart. That spread, or opening, is what we call an angle. We need angles to answer a simple question: how much did something turn? Builders used them to make walls straight, and ancient stargazers used them to measure how high the sun climbed. An angle is the first step to understanding right triangles. Picture a door. One edge stays fixed to the frame, that's our starting line. The door itself swings out, rotating around the hinge. The angle is how far that moving line has turned from the fixed one. We measure that turn. A ladder leans on a wall, making a right triangle with the ground. The angle between the ground and the ladder is the turn from the flat ground up to the ladder. If the ladder is twice as far from the wall. A common mistake is measuring the wrong pair of lines. Always check they meet at the corner. A quick trick: the corner is the hinge, the angle is how wide the door is open. Try it yourself: open a door. A right triangle is simply a triangle that has one corner exactly 90 degrees, a perfect square corner. The other two corners are always smaller, acute angles. We mark the right angle with a little square so you can spot it. Imagine a ladder leaning on a wall. If you know the angle it makes with the ground and the ladder's length, the triangle is completely locked. The height on the wall and the distance from the wall are forced. Every right. The 90-degree corner anchors the triangle. Pick one acute angle, say 30 degrees, and the whole shape is decided, the steepness is fixed. If you double the ladder length, the height and distance double too. Mathematicians call these similar triangles. A 10-meter ladder leans at 30 degrees from the ground. In any 30-degree right triangle, the height on the wall is exactly half the ladder's length. You can see it by picturing the triangle as half of an equilateral triangle. So, always sketch the triangle and mark the right angle with a square. The most common mistake is swapping the wall side and ground side. Always check which angle you're using. A quick trick: draw a tiny rough version to guess. In any right triangle, the hypotenuse is the longest side, always opposite the 90 degrees corner. Pick one of the other angles. The side it looks at is the opposite. The side that helps form the angle, but isn't the hypotenuse, is the. Imagine you're standing at one corner of the triangle, looking along the sight line. The side right in front of you is the opposite. The floor under your feet is the adjacent. If you move to the other corner, the names swap. The word a hypotenuse comes from Greek for stretching under. It stretches under the right angle. Opposite means exactly what it sounds like, the side the angle points at. Adjacent means lying next to. The adjacent side touches the angle but isn't. A 5-meter ladder leans on a wall. The angle at the ground is where we stand. The wall is the opposite side, it's what the angle sees. The ground is the adjacent side. The ladder itself is the hypotenuse. If the most common mistake is swapping opposite and adjacent. Always draw the angle first, then trace its sightline to the opposite side. The side touching the angle, not the HYP, is adjacent. Today, sketch a wheelchair ramp, label the hypotenuse, opposite, and imagine you have a right triangle with a certain angle. If you measure 2 of its sides and divide them, you get a number. Now, if you zoom in or out, making the triangle bigger or smaller, that number stays exactly there. This matters because it solves a huge real-world problem. If you know an angle and just one side of a right triangle, you can find every other side. It's like a magic key, measure the angle to the top of a tree. Remember similar triangles? They have the same angles but different sizes. When you zoom in on a right triangle, the angle stays fixed. All sides grow by the same multiplier, like photocopying a shape at 200%. Because both sides in the ratio. Let's find a tree's height. You stand 20 meters back. Your sightline to the top makes a 40 degrees angle with the ground. The tree's height is the opposite side, and your distance is the adjacent side. For 40 degrees, the ratio opposite adjacent is. The most common mistake is using the wrong sides. Always sketch the triangle and label opposite, adjacent, and hypotenuse relative to your angle. A quick trick, the ratio for an angle is just a look-up number, you don't calculate it, you find it. Imagine you're in a Ferris wheel car. As you go up, your height changes. The sign tells us how much height you gain for every unit you travel along the sightline. It's a fixed ratio, just like the tangent you already know. You already know the tangent ratio helps find a slope. But what if you know the length of your sightline to the top of a tree, and you want its height? The tangent can't help directly because it uses the adjacent side. We start with our right triangle. Pick an angle. The side across from it is the opposite, and the longest side is the hypotenuse. The sine is simply the length of the opposite side divided by the hypotenuse. As the angle opens. Let's solve a real problem. You're flying a kite. The string is your sightline, 100 feet long, at a 30-degree angle. We know sine is opposite over hypotenuse. For 30 degrees, the ratio is always 0.5. So the height, which is the most common mistake is grabbing the adjacent side instead of the opposite. Remember SOH, sine is opposite over hypotenuse. A quick trick, the side doesn't touch the angle, except at one end. Now you try, find a wheelchair ramp. Measure its. You already know sine, the just part of a sightline. Cosine is its partner, it measures how much of the hypotenuse runs along the ground, next to the angle. Tangent is the slope, how much up you get for each. Imagine a ladder leaning on a wall. Sine tells you how high it reaches, but not how far the base is from the wall, that's cosine. And if you're building a ramp, tangent tells you its steepness. Together, sine, cosine, and picture our spinning radius on the unit circle. Its horizontal shadow on the adjacent axis is cosine, it shrinks as the angle grows. The tangent is the slope of the radius itself. At 45 degrees, the opposite and adjacent shadows are equal. A 10-meter ladder leans at 60 degrees against a wall. How far is its base from the wall? cosine links the adjacent side to the hypotenuse. We know cos 60 degrees is 0.5 because the triangle is half an equilateral triangle. So adjacent equals. The most common mistake is swapping cosine and sine. Remember, cosine is close to the angle. The trick SOHCAHTOA helps. Sine equals opposite hypotenuse, cosine equals adjacent hypotenuse, tangent equals opposite adjacent. Try it yourself, find a ramp, measure its rise and run. Imagine a giant recipe book. For every angle, from 1 degree to 89 degrees, it lists the ready-made sine, cosine, and tangent ratios. Ancient mathematicians calculated these once, so no one had to redraw the triangle every time. They wrote them on clay tablets. Without a table, to find the height of a wall, you'd have to draw a perfect scale triangle and measure it every time. That's slow and messy. A table is like a preloaded app, you just look up the ratio for your. They started with a special angle, like 30 degrees, and drew a massive right triangle on the ground. By making it huge, any tiny measuring mistake became less important. They measured the opposite and hypotenuse, then divided to get the sine. They repeated. You're an ancient Egyptian surveyor. You stand 100 meters from a pyramid. Your sight line to the peak makes a 50 degrees angle with the ground. You open your scroll and find the tangent of 50 degrees is about 1.192. That means for every one. The biggest mistake is grabbing the wrong ratio from the table. Always sketch a tiny triangle and label the side you know and the side you want. That tells you if you need sine, cosine, or tangent. A quick trick, we want the height of a pyramid, but we can't climb it. Instead, we stand on the ground, measure a distance, and look up at the peak. The angle of our sight line and the distance we walked form a right triangle. For thousands of years, people needed to measure tall things, pyramids, trees, cliffs, without touching them. This method turns an impossible climb into a simple walk and a look. It's the same trick surveyors use today to map land and build skyscrapers. We know from our earlier lesson that tangent is the slope, the ratio of the opposite side to the adjacent side. If we know the angle and the adjacent side, our distance on the ground, we can rearrange the ratio. Opposite equals adjacent. Let's measure a real pyramid. You walk 100 meters from its base. Your angle measuring tool shows the peak at 40 degrees. You look up the tangent of 40 degrees in a trigonometric table, it's about 0.84. Multiply 100 times 0.84 equals 84 meters. The most common mistake is mixing up sine and tangent. Remember, tangent uses both legs, the opposite and adjacent, no hypotenuse. If you know the angle and the ground distance, tangent is your tool. Now go outside, step back from a tree, measure the. Imagine a clock hand of length exactly 1, pinned at the center of a grid. As the hand spins, its tip traces a perfect circle of radius 1. We call this the unit circle. Unit just means the radius is 1. Right triangles only let us work with angles less than 90 degrees. But a Ferris wheel goes all the way around, 180 degrees, 270 degrees, even 360 degrees. The unit circle lets our sine and cosine ratios grow up and handle any angle. Start with the point at 1, 0, that's 0 degrees. As the angle grows, the point moves counterclockwise. Drop a shadow straight down to the x-axis, that shadow's length is the cosine. Drop a shadow across to the y-axis, that's the sine. You're on a Ferris wheel with radius 1 unit. You start at the 3 o'clock position. The wheel turns you 150 degrees counterclockwise. Your height above the center is the y-coordinate of that point. On the unit circle, at 150 degrees, the point is. The most common slip is swapping sine and cosine. Remember, cos is close to x, cosine is the x-coordinate, the one you reach by going across. Sine is the y, the height. For a quick trick, sketch the circle and point. Trigonometry isn't just triangles on paper. It's the hidden tool inside your phone's GPS, the shape of a sound wave from a guitar, and the reason a bridge doesn't fall down. We use the same sine and cosine from the unit circle. Imagine you're lost in a city. GPS answers of where am I are by measuring angles to satellites in space. A piano tuner asks what note is that by looking at a sine wave shape. An architect asks will this roof hold by using. For GPS, your phone measures the time a signal travels from a satellite. That time gives a distance, which becomes the radius of a huge circle on Earth. With 3 satellites, you get 3 circles, they meet at one point, U. This is. A lost hiker's emergency beacon sends a signal. Satellite 1 is 20,000 km above Earth. The signal travel time gives a distance of 20,200 km. That's the radius of a circle on the ground where the hiker could be. Satellite 2 gives. A common slip-up is swapping sine and cosine. Remember, for a sound wave starting at 0, sine begins at 0, like a silent start. Cosine begins at its peak. Use SOHCAHTOA to keep them straight, sine is opposite over hypotenuse. Today, we started with an impossible measurement, the height of the Great Pyramid using only a stick and its shadow. We turned that dead end into a superpower by discovering that for any given angle, the ratio of sides in a right triangle. This matters because it answers the ancient question, how do you measure something too tall to climb? By turning an angle into a number, we can calculate any height or distance. This simple trick is the invisible foundation behind GPS, video games. It works in 4 steps. First, we saw that similar triangles lock in the ratios for a given angle. Then we named those ratios sine, cosine, and tangent. Next, we built a table of these ratios for every angle, so we could. Let's solve our original impossible problem. A surveyor stands 115 meters from the pyramid center and sights the top at a 51.8-degree angle. The tangent ratio links the opposite side, height, to the adjacent side, distance. We look up tan 51.8 degrees in. A common mistake is mixing up sine and cosine. Remember the chant, SOHCAHTOA, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Try it yourself today, use a tape measure and a phone app too.